in Idaho, that's in Rexburg, Idaho, and then went to BYU, which is in Provo, Utah. And then I went to the Naval Postgraduate School while I was active duty in the Navy, and that's in Monterey, California. And so I taught school in Utah for a couple of years. I taught math and science, so I was a school teacher. And then I taught in the Navy for about 4 years, taught nuclear power, did nuclear physics and reactor physics stuff. And then I did a transfer of jobs in the Navy, and I became a meteorologist, did meteorology, oceanography, work for the Navy. I have a master's degree in meteorology, oceanography. And I did a bunch of different things with that within the Navy. And because the Navy thought that it would be really cool, like if you are an oceanographer and a meteorologist, then you obviously understand science stuff. So they said, well, you would be really good at doing space stuff. So they sent me to manage space projects within the Navy. And so I got a bit of experience doing space project management stuff for the Navy. And so then kind of lucked into a position at retiring from the Navy. I think I lucked into a position being in NASA. It's not something I thought was going to happen. It's like, applying for jobs, like, hey, I think I could do that. Then I got hired. I was super excited. So I had wanted my cousins and stuff to help me, remember, like, remind me from when I was a kid. It's like, oh, you always wanted to work for NASA. I'm like, yeah, that's true, but never thought I was actually going to get there. So here I am. I actually ended up at NASA. I'm in the Heliophysics division. I will talk about what heliophysics is in a few minutes. And then I've had a couple of larger projects. Atmospheric Waves Experiment, that was actually launched in November. It's an exterior instrument that's mounted to the outside of the International Space Station. So the outside, a lot of people don't know that we have a bunch of instruments that actually are mounted there on the outside of the International Space Station. They have little platforms you can go up, just mate to it. It actually provides power and communications. So you can get quite a large amount of data from those instruments. And they can be there from anywhere from 6 months to 10 years or whatever, getting information and data. There's a lot of different spots on there that can actually point to the Earth. This atmospheric waves experiment is actually pointing down and measuring gravity waves. So any of you flown in an airplane? If you've flown in an airplane and experienced turbulence, you've experienced what's called a gravity wave. So there are waves in the atmosphere that mostly you can't see. We can see ocean waves because we can tell the difference in the medium. You can't really see gravity waves in the atmosphere because there's not a difference across there. But so that's what they're measuring. They're measuring at a specific wavelength that makes it easier to tell. And then another bigger project that I'm managing is it's called Punch. This is you have 4 different satellites. One of them is actually looking directly at the sun, and so it's a normal coronagraph. So coronagraph actually has an artificial eclipse that's on the end of the telescope. So it's intentionally blocking out the sun. But because of engineering challenges and can you point exactly accurate, you have to make your eclipse bigger than what we get to see on Saturday or on Monday. So it's a little bit bigger. So you actually block out more of the corona with that. So they have a coronagraph as one of them. And then they have 3 wide field imagers that they're taking pictures at the same time. So they're going to be able to stitch those together and get a really wide view of the corona of the sun, which we haven't really ever had. So we'll be able to watch as coronal mass ejections and other things come off the sun and progress out away from the sun. We'll be able to see those in real time as they go out. So, and I manage a whole bunch of smaller projects called CubeSats. I don't know if you guys have heard of CubeSats before. If you have questions, this is a small group. Feel free to ask the questions, okay? So, CubeSats, I don't think I have a good visual for that. So, CubeSat is a 10 by 10 by 10 centimeters. So 1U CubeSat's about this big, okay? Really tiny. So, CubeSats were developed to be able to have small satellites built by like universities and maybe high schools. There have been high schools and grade schools and universities and stuff that have all flown CubeSats. You put these in together until you have like a 3U CubeSat. So you have 3 of those units stacked together, called 3U. You could have a 6U CubeSat, so usually it's by 2 by 3, but you can have a long one, like a 1 by 6, so a longer one. And so those are CubeSats. They're really small satellites. So I manage about 20 of those that we're doing within Heliophysics. I've been married for 29 years, and I have 6 great kids. And all right, questions on me? Okay. All right, so awesome picture. We're going to get to this. All right, so total solar eclipse. Most of you probably know what a total solar eclipse is. So the moon actually passes in between the Earth and the sun and casts a shadow on the Earth. But because the moon is kind of, in relative, it looks the same size, right? Basically as the sun. Well, they're not the same size. The moon's pretty small. So it casts a very small pointed shadow. Because the sun is so huge, it casts basically a very pointed shadow to the Earth. And so for a total eclipse, that shadow is actually big enough for us it appears as though the moon is completely covering the sun. And for us, it will be, which is really cool for this area. For other places, they'll only get to see part of it. So outside of the path of totality, you'll only get to see part of that. And in October, there was an annular eclipse. So that's a special type of eclipse. It's a partial eclipse, but the shadow is not big enough. So it actually only covers most of the sun. So you end up with this ring of the sun all the way on the outside. It's called a ring of fire. It's really cool looking. I got to do that in October, which was really fun. Okay, so this is the path. We know where we're at on this one. So everyone should be wearing glasses. Okay, you're going to hear this probably every presentation. You should be wearing solar eclipse glasses. There are other ways of actually viewing the sun, viewing eclipse. So you could wear these and go out and look at the sun now. Okay, the filters on this will protect your eyes as long as you don't poke holes in it or something silly. Okay, so you can wear these anytime. Go out and look at the sun. So that's what makes it so that you can actually do that on an eclipse. Okay. Other ways are using like shadows and stuff. So this is cool. It's called a pinhole projector. This is from one of my projects. They built these specifically for this. So as the light passes through, it actually creates shadows. This one you have to play with a little bit. It's got 3 different shapes, so you can see the different shapes when you create a shape that. Well, as you kind of change the distance to focus, then you'll lose the shapes and you end up with just the picture of an inverted picture of the sun going through, and you see that. So that's what a pinhole projector is over on the right. Okay, so this is just an example of a pinhole projector you can hold up and do and play with. So. Okay, so this is our time frame for Niagara Falls. It goes for quite a period of time. So you have about 2.5 hours on Monday that you get to be out there. Anyway, so that's what we're expecting to see. It's long, so if it's going to be cold, you don't have to stand out there the whole time. It takes a little bit of time to progress through there. Okay, you can also do different things so this is basically creating a shadow. You can do different things with other types of shapes too. So it's interesting to see during the annular eclipse because the sun coming in, I end up with like almost a horseshoe effect. And so I end up with really weird looking shadows of myself. So I have pictures of some of my interesting shadows from that. That was really fun. This is not me though. All right, so NASA's doing some cool stuff during the eclipse. There's a lot of things going on, but this is one of the cooler things that we're doing. We're launching 3 sounding rockets. So a sounding rocket goes up. It actually puts something in orbit, not all the way in orbit, just goes up and actually comes back down. So it's only up in space for 15, 20 minutes. Maybe sometimes not even that. Depends on the trajectory they want and what they're trying to get. So they're doing 3 of them, so one 35 minutes before, one right during the eclipse, and then 35 minutes after. And that's actually being launched from the Virginia launch site, the Virginia launch location we talked about earlier. And so they're trying to explore things about the ionosphere, how the ionosphere changes during an eclipse.
So you're actually collecting data from the launches?
Yes. So when you do these sounding rocks, they actually have an instrument package on there. So they have specific instruments that'll be flying. And sometimes they actually transmit data, and sometimes they collect the instrument and then get data. So sometimes it's, receive data and store it on the instrument. I don't actually know if this one's trying to transmit during or if it's actually collect and store after. Okay, so you have a couple other ones that are of interest. You have a listening party using amateur radio. So amateur radio, anytime radio waves are passing through the ionosphere, this is another thing with ionosphere, then you get different changes through that. And so changes in the noise in amateur radio will come from that. And then they're looking for you have other solar radiation effects there. So, and then looking for some hotspots. So we're trying to see if there's if you can match magnetic hotspots with different features in the corona as well. Okay, so this is, you probably have not heard of the Heliophysics Big Year. So this started with so this is really advertisement. The sun is important. It touches everything. Okay, so this started with the annular eclipse. That was in October. Then we have the total solar eclipse we're going to have on Monday. And then we have Parker Solar Probe that's going to be having its close approach to the sun in December. So Parker Solar Probe is actually flying through the corona. You had to make a really nice big heat shield, and then the instruments kind of peek out around the heat shield to protect them. But so Parker Solar Probe can have its closest approach to the sun on.
How close to the sun is it going to be?
I had that. I don't remember now what it was. It was like, I think, 3 solar radii, maybe less. I think it might be less than that. So that's exciting stuff we're trying to do. So this is just if you look at the sun, so these are different wavelengths, so you can use different filters to actually look at it. So on the left, you don't have a lot of solar activity, a lot of sunspots. That's what it looks like at solar minimum. And then on the right is more of an example of what you would get from solar maximum with lots of different activity and sunspots. So heliophysics, we're trying to understand the sun. That's the purpose. Heliophysics is actually the study of the sun. How does it actually work? Do we know how it works? And how does it impact us and the rest of the solar system? So that's what heliophysics is. I only wanted to keep going back. Okay, so there are some different options if you wanted to get involved in some of the science. So you can go to our Eclipse website and you can look at different things. If you wanted to look at these and get some stuff, then participate in it. I'm a meteorologist, so I look at weather stuff. Yeah.
How do animals react when the solar eclipse happens?
That's a great question. Animals actually think it's night. So they will actually go through bedtime routines.
Oh, they're just sleeping stuff during the time?
Yep.
Wow, I'll have to watch my dogs.
So when I was at the annular eclipse, there was one of the park rangers there had a whole presentation on just how animals react to it, and they had pictures of elephants going to sleep. Like an elephant actually was standing there, went to a total eclipse, and they just tipped over like they were dead. It's really interesting. They actually go through what they think is a nighttime routine. It's time to go to bed. Yeah.
Is the relative rarity of eclipse, is that just because is the moon going around the Earth at a slight angle compared to our?
Yes. So so the moon's angle. The moon is on the same plane. So you guys know as the Earth and the sun. So the Earth rotating around the sun plane, where that is, the moon is slightly tilted off of that. So with that tilt, then it only comes into play where you actually create an eclipse. Yeah. So you actually get 2 eclipses every year. But most of them are partial eclipses, and they're not necessarily here. So you can have as many as 4 eclipses in a year. But most of the time it's 2. I don't know if that...
Do they have more eclipses on the moon because of the Earth?
lunar eclipses are a little more common, like total lunar eclipses, but it's still the same geometry problem. So, yeah. I think our ability to view a lunar eclipse is more common than, so you have probably essentially the similar number of lunar eclipses as you do solar eclipses, but our ability to view the lunar eclipse, because it's widespread for us to view it, is much more common. The angles work out better in our favor to view those. All right, so heliophysics, we're studying the sun. We want to understand the sun. So as a meteorologist, the primary input for any energy into our system, the weather system, is the sun. We don't really get energy from a lot of other things. So the sun is variable. It's not always the same. That would be really easy if it was always the same. Then there would be a lot of things that we wouldn't have to worry about, but it's not. So because it does different things, then we need to understand, well, how does that impact our weather? How does it impact, things that we talk about? You might have heard of space weather. Yes, we actually have space weather that we have to worry about. And then also we look at, well, how does it impact, well, if I'm going to go do something on Mars, well, how's the sun going to impact my stuff I'm going to do on Mars? Okay, so that's why it really matters. So the sun's actually always ejecting stuff. That's called the solar wind. It's like, we have these massive ejections, those coronal mass ejections. Those are huge, but it's always pushing stuff out. So it's like I don't know if it probably. I guess I think I have a visual on this that makes it a little easier. But so this is just orienting you into the solar system, or the universe, and into the solar system. It's a pretty cool video. All right, so here. Oh wait, it didn't work. Go back. Go back. All right, well, we'll just go to this. So the sun actually creates kind of its atmosphere around us. So a lot of people don't realize this, but so in the center here is our sun and our solar system with our planets. But it actually creates kind of a bubble around our planets, but it's impacted by the same kind of thing, cosmic rays, cosmic particles, and so it actually bends it like a kind of a bubble or something like that. So if you had a ship going on the water, it has a wake behind it. That's the same kind of thing. You get kind of this wake behind it. So the sun's creating kind of a wake behind it. So Voyager 1 and 2, which are actually part of heliophysics, the only things that we have right now that we've made that have gone outside of the influence of our sun. So they're actually outside of the heliosphere, or the sphere of influence of our sun. So this is theory, right? This is what it looks like in theory to us. Okay, so the same thing is happening. Okay, so that happens to our solar system, our universe, within the universe. So the same thing's kind of happening to the Earth. The Earth is actually getting these particles blowing into it, and it's being protected primarily by the magnetosphere. The magnetic field of the Earth actually protects us from all these particles and energy coming from the sun. And so it kind of pushes it around to the backside of the Earth, away from the sun. And when you end up with these coronal mass ejections, they'll come in and hit that, and actually the magnetic field magnetosphere has to absorb that energy. And so sometimes it absorbs the energy, and you end up with really cool lights in the northern lights. Those are all part of the response from the magnetosphere of the Earth, getting that energy deposited and then trying to correct itself into a neutral state, or back to a normal state. Okay, so just a couple facts about the sun. It goes through a cycle about every 11 years. It goes to a minimum, and then it slowly starts to build up a number of sunspots. It can go into, sometimes the pattern can be somewhat smooth and building up to like a solar maximum, and then it kind of diminishes back down to a minimum. But sometimes it goes through like multiple different peaks, and it's kind of all over the place. So, so that is over an 11-year cycle. It does that, and then the magnetosphere of the sun flips poles. So your north pole becomes the south pole, and starts over. So I don't know if does that make sense? Do you guys have questions? Do you guys have questions about this? This is what the sun is. This is what it does. Okay, so why? So really good question. Why does it actually have all these sunspots? Well, there's a theory that the magnetic field of the sun gets kind of wrapped around itself. We're trying to find out whether or not that is actually a valid theory. So, and then because the magnetic field gets kind of wrapped around itself, it interacts with itself, then causes eruptions of electromagnetic storms, pushing off stuff. It's like, okay, well that didn't work. It has to release energy, because if that's the case, then you're wrapping up all this energy within itself, and so it's getting tightly wound and has to release. So that's kind of the coronal mass ejections and the sunspots are created from this release of energy to try to correct its thing. So now, why does it actually go through like this peak and then come back down, kind of almost smoothly back down to well, why is it doing? Well, I don't know. We're learning about that, and we're trying to understand it. But one of the first steps is, well, how does it impact us? Is there any way for us to forecast when these coronal mass ejections are going to impact us? That was something we would care about. Okay, so these coronal mass ejections. So when I talk about space weather, you have this big electromagnetic ejection of mass that comes in and rams into the magnetosphere of the Earth. Well, what if it's a really big one, and the magnetosphere can't actually dissipate it and protect us from the whole thing? What happens? Do you guys know? Well, so then that electromagnetic wave actually impacts the Earth and impacts things that are electric. So I don't know if you guys know about this, but a long time ago, in a galaxy far, far away, we had telegraph lines across to use communication across the United States. Well, the telegraph lines are big, basically, thin wire power lines. Well, you had a big coronal mass ejection that actually came in and totally charged all of those and shut the whole system down. So we've had kind of big coronal mass ejections in the past that have impacted stuff that we're doing. They occasionally impact us now, but our system's a little more resilient now than it was. But anything you put in space is actually not as protected, and so you have to deal with that for spacecraft. And so.
When that's going to happen, so that there can be some preparations in place for that, and not really.
So, do we know when it's going to happen?
Yeah.
We might have a little bit of warning. So it depends. So coronal mass ejection can come off, and it can take several days for it to reach Earth. It can also just take several hours. Right. So there's a lot of things we don't understand about. Well, so we saw one come off. Well, where did it end up? Number one, where did it go? And how fast is it moving? So we have several spacecraft that have put up there that are looking more from the side, so you can kind of see how fast they're moving. Maybe if it's moving towards the Earth. So that's one of the reasons that punch is actually useful, is because you can actually watch the whole thing transition out to see how far and how fast it's moving. So that you can give some warning, potentially, of like, oh yeah, we know we had a coronal mass ejection. This is how fast it looks like it's going. So then we can give you some warning on when it's going to hit. So, yeah. It does. It varies a lot, and you know, you don't know until you actually get what's my next observation. Where does it show in my next observation? We don't have observations all the way across as well as it would be. It would be nice to be able to see from the sides.
Yeah, it seems like it would be hard to collect the data that you need then to make anything, any kind of predictions in the future if you're not having that consistently be the same.
Yes. So we're relying. So NASA, you know, we put up stuff and we try to baby it along forever. That's why Voyagers are still running, right? So they've been up there a long time. We have some chronographs that have been up there viewing the sun for this kind of stuff for a long time, and much longer than they were designed for. So most of these spacecraft are designed for somewhere between 3 to 5 years, not 3 to 5 decades. And we're, you know, almost completely reliant on stuff that's been up there for, you know, a few decades, actually. Yes?
Is there any way to get that information, like, directly from the archaeological record or like ice sheets or anything like that?
There isn't really a lot of good data on what the sun has done. I mean, we have some observations, but so our ability to observe the sun, you know, we actually have, you know, probably 400 or 500 years of actual like sun observation, but that was reliant on people, you know, using their eyeballs mostly, and you know, kind of crude telescopes and stuff to observe the sun. So you have to try to like, okay, well, this is what they were able to see. What would we be seeing in the same? And so we have to try to conjecture, like, well, we think this might have been what they were seeing. So there's a little bit of guesswork in trying to do some kind of equivalence to the observations we've had. So that's a challenge, right? We actually, you know, our ability to observe the sun today is significantly better than it was 20 years ago. And so then every time you actually put new spacecraft up, you increase your ability to observe. And so then you're like, well, you know, can I actually go backwards in time and try to figure out what it might have looked like before using the information I have? And so there's a little bit of a challenge with that. And so that's one of the challenges that the scientists face, is trying to figure out, well, how do I do that so that I can use that in some predictive manner for the future state of the sun? Yeah.
Does NASA share information with other countries and vice versa?
So all of our science data is open. So anyone can go in and get the science data. You have to have a big computer to try to use it if you want. So you know, you have to go in and kind of know what you want. But you can go in and get any science data that NASA's collecting has to be released to the public.
Other countries?
Well, other countries are considered the public, I think, at this point. So there's no, yeah. So everyone has access to it.
So you can all help each other.
Well, we do better at helping each other sometimes than others, but yeah. So understanding the sun, yes, I think that would be really beneficial. The more observations we have, but putting a spacecraft up to observe the sun is expensive. So
at this time there's no, like, it's just 11-year cycles that we're working, longer cycles.
Well, so you have the 11-year cycle that repeats. So it's a 22-year cycle because to return it back all the way. But we don't really understand the longer term cycle very well. So you go back and look at the pattern. I think I actually I have just kind of a snippet of like the last 100 years later in my presentation. But so it's hard to see, well, how's this pattern going to repeat? You know, so the longer term cycle is hard to understand. So this is kind of the space weather northern lights thing. So as it absorbs energy, that energy has to get deposited into, it gets deposited into the magnetosphere, and then the magnetosphere ends up being charged. Well, it's got to release that charge, and so this is kind of how, this is one of the theories on how that actually works. That the magnetic lines actually close around each other again and deposit that energy back in. So as it comes down in here, as these magnetic field lines come in here, they have corresponding electric field lines that go with them. And what those look like, the shape of those, is actually would help us understand a little bit more about this process. We have a spacecraft that's actually going to be observing that process. How do these field lines at the North and South Pole, how do they actually reconnect, and what are they shaped like? What do they actually look like? So we have a project called EASY that's actually going to be doing that. And that's one of those small satellites. It's three small satellites, 3 6U satellites that are actually flying along, measuring those. So that's supposed to fly later this year. I think it might be pushed until later, but so we'll see. Hopefully we'll understand that process a little bit better.
What is that pinching, where the energy is?
Where it pinches there?
Yeah.
So the theory is that it gathers that energy, and then so it actually closes the magnetic field line on itself. And so I don't know if that's the theory on how that works, but is it because you got so much energy you actually created extra magnetic lines as well, so that it could actually recombine and dissipate the energy, and then it releases and goes back to a normal state? That's a pretty real possibility in this case. Okay, so these are some other pictures that we get from different observatories we have up for the sun. So you have the northern lights. These are all part of the auroras and that deposit that energy. When you have a really big coronal mass ejection, the auroras will actually be viewed further south. So there was one just a couple weeks ago. I think you were supposed to be able to view here if you had a clear sky.
We had a really pretty sky a month ago.
Yeah, so as they come further south, you know that the energy being deposited is actually more energy. So you're actually going to see the result of that as you're with it here. Okay, so this is more of a long-term cycle of the sun. So you can see kind of the general pattern, right? Over from so this is a little over 100 years. You can see cycle 19, had a lot more solar activity. What caused that? We're trying to understand. And so we're looking at we have kind of a peak coming up here on 2020 in the 25 cycle. Well, it's a little bit higher than what cycle 24 was, but it's much lower than 23. And so, we have this massive, we still haven't even reached the peaks of 21, 22, and 23, which were a lot higher. So, huh? Almost. So you can see kind of 3 there, 3 and then lower, and then 3 and then lower. But from the longer term observations, you have periods of time where you went to almost 0. So you had 2 or 3 cycles in a row that were near 0. They had almost no solar activity from the observations we have. But those are from a long time ago. So what caused those? I don't know. So in one of these more recent ones, you had SpaceX was actually up here on the top right. SpaceX was launching spacecraft, and SpaceX, in the way they're doing this, they launch into a low orbit, so they can check out the spacecraft, make sure the spacecraft are functioning, and then they raise them into the orbit they're going to actually operate in. So they put them into more like a 300-kilometer orbit. Well, while they were sitting there checking out all the spacecraft, you ended up with a coronal mass ejection that caused some superheating of the atmosphere, and so the atmosphere expanded a lot. With this superheating, then it increased the drag on the spacecraft. So just like if you're going through the air, if you increase the density of the air and increase your drag, well, it's going to slow you down. So the same thing happened to these, slowed down a bunch of these spacecraft, and they lost most of it. So, yeah, so space weather impacts, so now we're doing a lot of communications through satellites. Space weather actually impacts our communications. So if we're reliant on GPS for navigation, so you guys use GPS for navigation? Well, if you're reliant on GPS for navigation, anytime there's a lot of high activity in space weather, that disrupts the GPS signal as it comes through the atmosphere, and so it's going to put you off your location. It's not going to necessarily be accurate. So I don't know if you guys are aware that that actually happens, but anyway, GPS navigation is really cool when it works. Anyway, so that's an important part of this, that how it applies to you in your life. All right. So we want to explore the fundamental processes that's going on inside the sun, as much as we can observe that. So Parker Solar Probe is really kind of key to that. We've never observed inside the corona. In observing inside the corona itself, finding out, well, what does that structure look like? Well, the structure looks very different than what we thought it was. We kind of, we pictured, I think that in all of our modeling and stuff, we try to simplify things in our modeling. That's the way we do it. Otherwise, it's really hard. So if you simplify things, then things become spherical and they're really nice and smooth. Well, the corona is not spherical or smooth. It is got all these waves and bumps and stuff like that in it that were not really expected to the magnitude that we found. So, we're learning all kinds of things about very close in, and then we're learning, well, how do we interact with the rest of the universe with Voyager 1 and 2? And a lot of this really, we want to understand, well, how does it impact us? So that's important for us. How does it impact us? And how does it impact us, the rest of our universe, or the rest of our solar system? If we're going to put stuff on Mars, I want to know, well, how is the sun and that going to interact with the Mars system? Are we going to understand that well enough to be able to protect ourselves or the equipment we put there? So those are all things that we're trying to understand. And so for heliophysics, we're putting spacecraft around Mars specifically to understand how it is impacted, its magnetosphere and everything around Mars, because understanding the Martian atmosphere and how it's interacted there will help us also with understanding how Earth works. So that's actually supposed to happen this fall. Yeah?
December 24th, when that probe goes,
It'll go through again. So it's been through several times. Yeah.
is it televised, or is it something that we can watch on your website, on the NASA's website, or will we video?
So so to be able to get communication back from the probe, you have to wait for it to finish passing through. So our ability to communicate with Parker Solar Probe is delayed. So it starts its transit, and then we know where it's supposed to be, and we can kind of, sort of follow where it's at. But then we lose communications with it because the coronosphere actually interferes with all communications off of it. So we have to wait for it to finish its transit around so that we can actually then download the data and get the information. But you could follow it. So there is a website for that. You could actually follow where is it at. So if you look up where Parker Solar Probe, it actually will tell you where its current location is. And yeah, you're welcome. All right, so this is, let's see if this will go. So this is kind of a myriad of all these heliophysics satellites that have been up, taking measurements across the solar system. So Wind and SOHO, those are actually out further away, so they kind of stay in the same location so they can take constant images of the sun. So stereo A and B were actually put up in orbits to go around the sun slowly, so you could get kind of the side views. And so then you have Parker Solar Probes going in there. Solar Orbiter, which is taking some really cool imagery of things. And then you get further out. just kind of a visualization of where all those satellites are. They're trying to take imagery of and measurements of our heliosphere and all the things that are in it. So.
Do they try to collect the old machinery to bring back, or just move it?
All right, so that's a really great question because we really can't deorbit things very well. It would probably cost us more to try to go get any of those pieces of equipment than they cost to make.
When they stop, do they just fall to the earth?
It depends on what orbit they're in. So this is a fun part. This is a fun question. So anything that's in low Earth orbit, so close to the Earth, will eventually deorbit and come into the atmosphere and burn up in the atmosphere. So anything that's closer in. So closer in really is anything less than about 700 kilometers up. Most of the satellites we're putting up, Starlink, all those satellites, those are all less than that altitude. So they will all deorbit within some period of time. The higher up, the less drag, the longer it takes to deorbit. So this International Space Station is around 400 kilometers. We launch little satellites off of the International Space Station regularly because it's really convenient. But they'll last anywhere from, a few months to a couple years. And it depends on whether or not they can, what kind of drag they have. So most of them, it just takes a while to deorbit. There's an effort to try to get people to try to deorbit their spacecraft faster, if possible. But a lot of the smaller satellites don't have reliable propulsion to be able to do that, so they can't force themselves to deorbit very well. So then you go out further. The GPS satellites are in what's called a MEO, or a mid range orbit. Those will never deorbit on their own. You'd have to actually intentionally use propulsion to deorbit those. And then you have geostationary satellites. So we get some of the greatest imagery we get for meteorology from our geostationary satellites because they can actually just keep taking pictures of the same spot. So they're at a high enough altitude that they actually basically hover over the same location on the Earth all the time. So they sit there basically and can point at the same spot. So that's why geostationary is actually really beneficial for observations of the same kind all the time. So we have quite a few satellites in geostationary orbit. There's a lot of communication, but weather satellites as well. So those don't deorbit on their own either. But that's a very specific orbit, and so anything that's there has to actually go into at least not in the same orbit. So they usually raise the orbit a little bit so they're outside of the specific geostationary belt. So they call it a geostationary disposal orbit. And they put them there so they're out of the way, right? So yeah, a garbage orbit, right? So they put them out of the way where people aren't going to use it. That's their kind of. We got to put it far enough away that it's not going to cause any problems. But you have all kinds of things. So if you want to put something around the moon, then you have a lunar orbit. You have really weird orbits that we're going to experience with Artemis to put things around the moon. And so, I don't know, did that answer your question really quick? All right, so this is kind of an image of what it would look like. This is a model of what it would look like to have a corona mass ejection come off the sun. Okay, so you have just kind of a general picture of the solar system over there on the left. Okay, so since the sun is spinning, also, then things coming off the sun are also going to come off spinning. They're going to come off in a different direction. So this is one theoretical model of what that looks like as these coronal mass ejections come off of the sun. So I don't know. I am not super familiar with the model. Do they have all the planetary rotations in here, or do they just kind of assume you're kind of stationary while we just work on the sun stuff. You know, there's a lot of things they could have done with that.
Do the planet revolve in the same direction that the sun rotates?
Yes. But not as obviously not as fast.
Yeah.
Yeah. All right. So this is just kind of another way of looking at some of the heliophysics missions that are on here, that have been out there where they're taking observations. So. Oh. So this is the atmospheric waves experiment. I talked about that one. I don't know if you guys have any questions about it. So they're actually observing at about 90 kilometers. There's actually a glow that's actually emitted from the Earth at a specific wavelength, and so they're taking measurements of that, what's called air glow, and measuring gravity waves in that. So they'll be able to do that for a couple of years. And this is Punch. You have 4 small spacecraft. These are not considered CubeSats, but they're really not a ton bigger than a CubeSat. They're more like probably closer to a 3x4 U, so, you know, about this big. So, really not a huge spacecraft. We're about a year from launch, so going into testing. You have to test the spacecraft to make sure it can handle the environment before you send them up into space on a launch vehicle. So getting stuff into space, strapping yourself to an exploding object that will launch you to space, you have to be able to actually withstand the environment that you're launching in. So if you watch any astronaut movie, you know, they put them on there, launch is really tough. It's tough on the human body when they do that. It's tough on spacecraft. So anything going up to space has to withstand a lot. I would totally love it if my kids have told me no. Nope, you're not going to do it. So that's Punch. So one of the cool things that happens. So NASA doesn't actually have space weather forecasting responsibility. That's a responsibility for NOAA. So NOAA has weather forecasting. They have space weather forecasting. So a lot of the NASA satellites that have been used to observe the sun or get information from the sun, if they can be used in a more operational way. So if I want to do weather forecast, I need to get the data more quickly, right? So if they can do that, if there is a way to do that and get the data in a way that NOAA can use it more quickly to provide forecasting, then they will do that. So that's happened for many of the NASA missions. If they can, they will increase the data flow or make it so they can get it more on an operational type cadence. So they can use that to help with their space weather forecasting.
So this satellite in the corona is going to pass through, send some information back, and then go into the sun, right?
Right.
Can't break the gravitational load.
So eventually, so this one is going to, so they have control of it while they still have propulsion. So they can control its orbit to make sure it doesn't just like end up right in the sun the first time. So if it can and continue to do passes through the sun, it will continue doing passes through the sun as long as it is probably capable and we can afford to do so. Once it runs out of propulsion, then it would not be able to alter its trajectory sufficient to escape the gravity of the sun. So eventually it'll end up in the sun. But when that has not been determined yet. Because we still have control over its orbit. I don't know if that answers your question or not.
It's not coming back.
It will not come back to us. No. We're not going to be able to go back and get it, retrieve it, and try to use it again. That's right.
So how much data will you actually, you'll get the data until it's no longer.
Until it no longer can function, or we can really, so we've had a couple of satellites that just recently stopped being able to work. So, you know, I don't know. You guys all carry around electronics, right? Probably. So, well, you replace your cell phone a lot more often than we replace satellites, and so we try to get them to operate as long as we can afford to do that, and they still function. And then, you know, depending on the orbit they were put in. So if they're in a LEO or low Earth orbit, then they will deorbit eventually. But any other orbit we put them in, then they become part of the system. Or they crash into something else like the sun. But most of them are going to be in the gravitational pull of something, some object, right? So you have a couple of different orbits that are actually really fun that you can put the satellite there and actually stays basically in kind of a stationary orbit. So you have L1, L2, couple different orbits that are nodes. So like if you put something in there, then it just basically hangs out in there and it retains the same, essentially the same direction on the sun all the time in relationship to where it's at the Earth. So it stays basically, draw a triangle. That triangle basically stays the same all the time. But so you have a few different things like that, but all of them become part of the orbit or the system. All right, I think I'm mostly out of time, but so this is one of the other ones. This is the other one I talked about. This actually measuring how that energy is deposited and what the shape of that energy deposit looks like as the magnetic electric field lines come in and deposit energy in the northern, with the northern lights. What do those field lines look like? Because understanding, so from a physics perspective, if I want to understand how something works, I have to actually understand the really basic physics processes. And if I understand the basic physics process, I have to be able to describe how things are actually going to move. Well, if I can't understand how they move, I really don't quite understand the processes yet. So for this, there's a lot of things about this that will help us understand what are the basic processes that are happening here so that we can better model how it's actually functioning in the future. So that's the purpose of this one here. And this is kind of a snapshot of a bunch of the different projects that we have out there that are doing heliophysics science. If you have questions I haven't answered. All right, well, I will be around in different places, all weekend. And there's lots of other people that are going around doing different talks all over the place. So I think everybody has different things they're talking about. You'll probably get a very similar, this is what Eclipse is version, but then everything after that I think is all kind of their own specialty, whatever they're working on. All right, cool. Well, thank you for coming.
Thank you.